You can see my screen?
Yes, sir.
Okay.
It's visible.
Yeah. So this is just what I showed in the class as to just to give an idea of where we are. Okay, on the right side. Um, See, normally I would, okay, we've introduced, I mean, I'm showing you transition systems and how bounded model checking works and getting into CBMC about how exactly it encodes the behavior of the program as parts, symbolic parts, using the SSA notation and the notion of specifying your pre and post conditions, okay, in terms of assumptions and annotating your program with assertions and so on. Uh, the basis, the logical basis for all these things that we have been discussing, the concepts and some of the techniques, they're grounded in um, some early work in the efforts in using logic to not only describe, I mean, to model or formalize, model formal semantics of programs. And the first logical system, a complete logic system that people were worked on and introduced uh, to prove programs correct, much like you have propositional logic and first order logic and different kind of logics that define a set of inference rules that can then be used to prove theorems that are true, that are valid in a particular logic. So the idea was, oh, can we not do a similar thing if once you model a program as an object in some kind of a formal logic, is it possible to introduce a set of inference rules uh, such that you could instantiate those rules and just like you can prove theorems through as instantiating inference rules, can you not prove the program to be correct given with respect to a specification? One such thing was a system that was invented by a guy called Hoare, Christopher Hoare. And that is what I will introduce. And you will see once I introduce that, the inference rules and the way proofs are constructed in that logic, program proofs. By program proofs, I mean proofs of correctness of programs that show that a program is compliant with a given specification. You will see that a connection between what CBMC and then in any verification tool that you will be coming across will be using internally to to automate those proofs. Basically, CBMC and Euclid are automating the proofs of correctness that one can see as being constructed in inside Hoare logic, and that's why it is important, when you study formal verification to understand Hoare logic, and that's what I'll be introducing to you today. Okay. Oh, before I did that, yeah, last time I mentioned that I wanted you to give an example as to why even symbolic execution, a bounded model checking, though even in the form in which they are being used in an incomplete way, it is still better than uh, testing by simulation. So this example gives is a good example to illustrate that. So it's a simple thing that the code is expected to return the absolute value of a given input. And in there, it works mostly correctly, except at some corner, for some corner value of x, some corner value, it does not. It returns uh, the wrong values. You can see it returns the negative value, even though when it is positive. So if, when you simulate it, you can only simulate and test the program for specific inputs. So even if the specific, whether you find this bug or not depends on what value you test for. If you luck, then and choose that particular value, you could. Otherwise, so if you randomly tested this over random inputs by choosing the inputs randomly, then the probability of finding this bug is very small. Okay, it's 1 in 2 to the power to the minus 32. But if you use symbolic execution or bounded model checking, you're sure to find this. Actually, one unrolling of this, in this case, since there's no loop, one unrolling will actually find it. Okay. Why so? Can anyone answer? Why will, if you use bounded model checking, this is guaranteed to be found? You guys there? Let's see. I'll see who.
Yes, sir. I
Ah,
mean, doesn't bounded checking check for all possible inputs or something?
yeah, that's correct. Okay. Was that Sawmill or Lucky?
Lucky, sir.
Okay, yeah. So that is the correct answer. So symbolic execution and bounded model checking, for every unrolling, what it does is it checks for all inputs. Okay, that is as simple as that. Okay, so since it checks for all inputs, then so it is guaranteed to find this. That's exactly correct. Are people convinced? Okay, that is the key. That for each unrolling, it it has the effect of checking for all possible inputs. So it checks the validity of the assertion. And how does it check that? It takes the negation of it and then sees if it is unsat. If it is sat, then there is an error. In this case, it would reveal that. So the effect of checking unsat has the effect of checking for all inputs, and that's why it is. I think. Okay. Uh, yeah. So that's the key here. Okay. Yeah. So let me change tack, then go full board. Okay. So yeah. So I'll choose a small toy programming language like we had seen earlier. Okay. To introduce HoareLogic. I know some of you who have taken my the ML course, you would have seen that is so when I make it interactive and ask questions, yeah, so there's some material you would have seen this material before. The others maybe it is new, or maybe you have studied HoareLogic in thing, but bear with me, and you will. So you can add to if you've already seen something and you see something different coming from me, you can raise questions. Okay, so it has two primitive statements, skip and an assignment statement, and usual composition, sequential composition of commands, and a conditional command, okay, and a loop, a while loop to construct loops, okay. So you've already seen, okay, that what do we mean one way of answering this? Okay, what it means to say that program correct is to give a precondition which is a constraint on the possible inputs, and give a post condition at usually exit points, or you can insert these in the form of asserts, and that's what happens in CBMC. And then you which and the post condition describes the expected condition when the program reaches its exit point. And you might want to you can define correctness as saying in every time for all inputs that satisfy your precondition, your post condition, when it if and when it reaches that point, must hold good. But are these the only? That is how we have been seeing it in all the asserts and specification for transition system have been. I mean, at least for sequential program, it has been. We have in CBMC on examples we have been using this notion of correctness. So one can ask the question: are these the only things that we want to prove about programs? And is this the only notion of correctness? The answer is obviously no. There are lots of other kinds of behavior that you might want to ensure. For example, what is the worst case time that it uses? What kind of resources it uses, and it does it. The time and resources are within the expected bounds. Okay, that can also be something about you want to check about program behavior. And yeah, and we have already seen that sometimes you want to show that things hold for all point, forever. That is usually used in concurrency, and things always something can must need to happen eventually, and so on. So there are various other things. So when you insert this pre and post condition in terms of assertions like you're doing in CBMC, that checks one aspect of correctness, but there can be other aspects of correctness that also need to be addressed. But for now, we will stick to that input-output correctness that we are say that we that stick to that and see uh, how that can be formalized and proved using this logic. So that's what I wanted to do. So given that, even there, when you're talking about input-output correctness of sequential programs, there are subtleties that you need to address. So given this program, ask this question: if is this correct? And if so, why? What do you think this program is doing? Saumil?
So is it computing one times, two times, three, all the way till a given x?
Um,
It seems like factory.
yeah, factorial
Factorial, yes.
is one thing. So before you answer this question, I mean, yes, okay, so there are things, and that's why I'm trying to motivate. Look, I mean, you will have to specify the behavior, or it could be that if yes, okay, so one thing is it has to be relative to a particular expected, I mean, post condition, okay, so and so you'll have to specify that. Even then, there are, okay, if you say that it is expected to do it, then but there'll be, is it expected to compute this for all inputs no matter what, or it is for some constrained input assumption. So you need to specify the input assumption also. Does it compute this factorial for all values, for all input values in this case? See, x here is unconstrained, okay? And if x is negative, if x is, yeah, does it terminate? That's also a
No, no, no,
question.
no.
Um,
No, sir. If X is negative, then I don't think so it terminates because Z is increasing and it won't.
that's that's correct. Therefore, so
So do we put a precondition of x being more than or equal to 0?
yeah, you could do that, okay? Then it does terminate. But the point that I'm making is when if I specify this post condition as this, it really it what does it mean? If you define the correctness as, oh, if and when it terminates, then it has to satisfy this, the given condition, if and when it terminates, okay? Then even when it then it is indeed correct, because for negative x's, for all x's that are non-negative, indeed it computes the factorial. For negative, it does not terminate, okay? So if your notion of correctness includes that it needs to terminate, then it is incorrect, okay? But if that is not the case, if you interpret the correctness with respect to this post condition as, and that's how we have been interpreting whenever we introduce, insert, annotate at a particular point an assertion, a program with assertion, means that every time it reaches that particular program point, that condition the given condition has to hold good. So if it is not terminating, you could view this as being correct because you never reach the exit condition, okay, and therefore it is still correct, okay. So you'll have to define the notion of what correctness is. So even with this pre and post, when you limit yourself to this pre and post form of correctness of sequential program, there is two notion of correctness. One is and that's usually called partial correctness here, which does not care about termination. It defines it as give it, for all inputs that satisfy your input assumption, that is the precondition. If the program terminates at all, then this postcondition has to hold good. Okay, that notion is called partial correctness. Okay, and with relative to that notion, this program is indeed correct. And the other notion of correctness with pre and post is what is called total correctness, that your program for every input that satisfies your precondition, the program must terminate, and when it terminates, it must satisfy the post condition. That is total correctness. Okay. Uh, that's what we will define two notion of correctness. Of course, there are lots of other, even without pre and post, you can define correctness conditions that are very relevant in practice. For example, yeah, I don't care about pre and post. Okay, any program, correct program ought not to overflow, okay, or underflow. And if they're manipulating pointers, they should not be null dereferencing. There are lots of runtime conditions, usually runtime errors that your program you would expect not to cause. Okay, so there are techniques even without pre and post to ensure that these kinds of runtime errors that you expect any program to not violate can be checked as well. Okay, so but of course, those kinds of errors, runtime errors, can also be specified in terms of assertions, and then that ensure. Okay, but the key takeaway that I wanted to get from, to introduce is these two notions of program correctness, which can be specified in terms of pre and post condition. And okay, so another example. Okay, just to show you this post here, the post condition, say I have n is equal to 1. Okay, now is that what are some of the preconditions? That's another way if you can pose, given the notion of correctness that I've defined. Now I can ask, what are some preconditions for which this post condition is true? Okay. So obviously, this for every I mean, if there n that is power of 2, this condition holds good, right? If it's,
Yes, yes. Yeah.
yeah. But if you think about it, if you're using the partial correctness notion, this post condition, if your notion of correctness is partial correctness, that you don't care about termination, then this program is correct with the precondition can be anything. Okay, that is the weakest precondition because for any other value that is not input value, that is not a power of 2, I claim that this is this even true for every possible n? That depends on obviously whether it is because whether it terminates or not. Okay, that question depends on the termination. But in this particular case, it doesn't matter whether it terminates or not. That's because you can actually argue it terminates only when n is equal to 1, correct? Okay. So, so certainly it's partially, definitely, based on partial correctness. N is equal to 1 is always holds when and if it exists. Okay. It doesn't matter what happens in the body of the loop. So with n is equal, when, if at all it terminates when n is equal to 1, at which point the post condition will hold good. So regardless of whether this terminates or not, it always holds good. But does it always terminate? Does this always terminate?
Smoking gun.
Yeah, I didn't hear that. So let me ask specific. Reinhotter, does it terminate?
I'm not sure, sir.
Yeah. So this is actually an open problem. Okay, you're right, Ryan. So see, what happens is every time if it is odd, if it is even, obviously this terminates, correct?
Yes. Uh, no, if it's a power of
Power of
two, then
two. Yeah, you're right. If the power of two, it terminates. Otherwise, what it does is, yeah, but what it does is, if it is odd, then it multiplies by three and adds one. It it does terminate only if for any particular n if such a sequence of numbers, okay, so if it is odd, then it adds three, I mean, multiplies by three and adds one, which makes it even, but then it can produce, because of this division by two, it can do. So it actually depends on whether the series for any particular n, the series of numbers that it produces, if it ever converges to one or not. See, this is a very kind of a clever way of setting this thing up, and and this termination of this program, it very much depends on whether that series of numbers that it produces for any particular input n ever converges to one. And that series of numbers is apparently called Collat's series. And this is also this issue's problem whether that series converges to one is an open conjecture called Collat's conjecture. Therefore, it is not, Reinhardt's answer was correct. Okay, it is not clear if it terminates or not. So, in order to ensure that it terminates, you will have to, have a proof that for any n, this series of numbers that it produces as it executes that while loop, if it ever converges to one or not, which is indeed an open problem. Therefore, proving termination is much harder. Proving total correctness, which includes termination of programs, is much harder than proving partial correctness, which just asks the question if and when it terminates, if a given post condition holds good. Okay. We will look at termination also, but in today's lecture, we will be addressing partial correctness. Okay. Good. So how is correctness, these two notions of correctness defined? So for every sigma, where sigma is a valuation for the variables that are used in the program, for every valuation that makes the precondition true, that's what it means when I say that satisfies the precondition, if the program terminates, with and when it terminates, if the valuation for the variables are sigma prime, then sigma prime satisfies the given post condition. Total correctness, as I've already said, for every sigma that satisfies the is defined as follows. For every sigma that satisfies the precondition, the program must terminate, and the valuation sigma prime that you get when it terminates satisfies the post condition. Okay. A few historical notes before yes, is there? Okay, that
I
is,
would like to clarify, sir.
yeah.
The only difference between partial and total correctness is that partial correctness, the program may not terminate, but in total correctness, it has to, right?
Yes, that's correct. That's a
Thank you,
difference.
sir.
Whereas in both cases, the post condition has to hold good. So in the first case, if it does not terminate, that case it is vacuously true. Yeah. Hmm? For partial correctness. Yeah, yeah, you're right. So the notion is whether it terminates or not. Um, yeah, so for a few historical notes, this particular logic that I'm introducing was first proposed not as a logical system, but in it's kind of an informal way. It was proposed in 1969 by Floyd, or probably, I mean, the logic was proposed in 1969 by Hoare, but some notions were already proposed in 1967 by Floyd. That's why sometimes this logic is called Floyd-Hoare logic. Okay, and it is presented as an axiomatic semantics of program. Okay, and there are two very well-established ways of defining program semantics. That is, mathematically or logically characterizing the semantics of programs. One is called operational semantics. The other one is called axiomatic semantics. The analogy is you can have compilers for programs, programming languages, or interpreters. Okay, there are two ways of implementing program execution. Similarly, the semantics can be given operationally or axiomatically. Whole logic is an axiomatic way of defining the semantics of program, what exactly it means, the various concepts of program. But it can also be the advantage of this. Both of them can also be used as a basis for constructing proofs of correctness. Okay. Um, First I'll do Hoare logic, which is like an axiomatic semantics, and later I will also, for the sake of completeness, talk a little bit about operational semantics in later class. Okay, so Hoare logic is based on this basic judgment. This is the atomic formula of this logic. And that is a Hoare triple. This is like a basic judgment. Okay. So here, Hoare triple consists of three components. Precondition, which is an assertion in some logic of your choice. For the purpose of this lecture, we will assume that this P and R are formulas in a chosen logic. We'll assume that we'll be using first order logic. And Q is a fragment of program in your in whatever programming language of your choice. Okay. So P and R are formulas in some logic, and Q is a program. And this Hoare triple, as when viewed as a formula, is true if whenever this statement is true. If the assertion P is true before you start executing the program Q, then the assertion will be true on its completion. Okay, what does that mean? Okay, more precisely, if Q starts in a state satisfying the assertion P, and if Q eventually terminates, then the final state is guaranteed to satisfy the assertion R. Okay, so this is what a Hoare triple is. So this is for partial correctness. That is, more formally, for every x and y, if px is true, if the precondition is true, and the program Q terminates on x, if it terminates on x, then R holds it. So this formula, so this Hoare triple will be vacuously true. This is the Hoare triple for partial correctness. Okay, so this will be vacuously true, as you know, if x p does not hold good for p. I mean, if p is false, for example, obviously this is vacuously true. Or if it does not terminate in those two cases, this is vacuously true, regardless of what r is. You can have a similar Hoare triple that captures total correctness. And since I said that we are building Hoare logic today, introducing Hoare logic for partial correctness, this is the atomic formula of Hoare logic. Okay. So any questions here? So I'll give you some examples of Hoare triple, and then I'll ask you. Okay. Is this valid Is this whole triple as per the definition in the previous slide valid? Let me ask somebody who's here. Um, who? Yanishri, are you there?
Oh, yes, sir. Am I audible?
Yeah.
Okay.
Okay, so yeah, if you start from a state where x is greater than or equal to zero, obviously, since you're incrementing, it is true, correct?
Yes.
Yeah, skip as per the semantics, skip is a null statement, okay? So that is the intended semantics of thing. It is supposed to be a no op. So is this true?
No, sir.
Yeah. Why?
Since in the precondition we are just limiting x, but we are not talking not saying anything about y.
Why?
Hence,
Because
y can
why, the
be.
precondition is not constraining y is not constraining y at all. So it includes both the case where y can be in a negative as well. And then since skip does not do anything, this is not true. So now I'm asking the question, uh, if this is true. Anybody want to take a crack? Yeah, people that have taken I want the people who have seeing it for the first time, okay, to give an answer. This, some people who have listened to my previous lecture would probably know, like Lucky and so on. So I'm asking,
So what does the double question mark mean?
yeah, I'm asking you, what is a post condition that makes this whole
Why
triple whole triple be true?
y greater than equals x?
Yeah, who's this?
Sir Soumil.
Okay. Why?
Like if x is less than y, then it obviously holds. But if x is greater than equals y, it will reset x to some y. So it is going to limit it to y.
Yeah, that means then you are actually the opposite of it. So it makes sure that x is always less than or equal to y. Is that what you said? You said the reverse, no?
No,
Yeah.
I said this.
Huh?
I think I said this.
Oh, okay. Then it's correct. Okay, because if x is greater than y, it makes x is equal to y. In that case, x is equal to y. If x is less than y, it doesn't do anything. Therefore, it leaves it as is anyway. So it is indeed x is less than or equal to y. That's correct. Okay. And how about this? Here I'm asking the question, what is a precondition with which, if you started, you're guaranteed to have end up in a state when that x is greater than or equal to y?
Sir, I had a question in the third one.
Yeah.
Hello. Can just true be also one of the post conditions? Just true.
Can?
Just true, sir. Just true be one of the post conditions. Since we are adding true as a precondition in the, can't we just add true as the post condition to make it true?
See, if you had true as the post condition, no. See, it'll allow anything, okay? So true, okay, you can start, since your precondition is true, which means that x and y could be anything, okay?
Oh,
So
okay,
let's
okay,
suppose
okay.
x
Yeah,
is greater than y, then it forces your post state to be where x is equal to y. Okay, so if you did true cannot be, yeah, it'll be wrong to have true as a post condition. Yeah,
Perfectly.
yeah. So you could, yeah. So this x has to be less than or equal to y for this in this case. Yes. Okay. Yeah, it cannot be the case. Okay, let's get to this. Anybody?
So the same condition holds as the precondition as well, right? Oh, x is greater than equal to y.
Um, but the same condition x. Oh, you mean the same post condition? Yeah. Yeah.
No,
So
I'm saying
here, if x is uh, if x is less than y, x is equal to y. Okay. So there are several things that you could do. Yes, you're right. Okay. Whoever answered x is greater than or equal to y is certainly true. But you can also have where x is equal to x and y is equal, right? Yeah. See, there are various possibilities here. If x is less than y, yeah, I mean, you can have some specific x is equal to anything where x is greater than or equal to y, okay, is certainly a possible input condition. No, one thing you could be, you can make x is equal to 2 and y is equal to 1, or x is equal to 2, y is equal to 2. You can also make it more specific. Okay, so uh, but among all the predicates that makes this whole triple true, x is greater than or equal to y is the weakest of all the predicates. Okay, and that's why this particular, so in general what I'm saying is the hot triple, when you ask these kinds of questions, there will be possibility several candidates of pre and post conditions. So in this case, yeah, I'm asking for a precondition, and here x is greater than or equal to happens to be the weakest, in the sense it captures all possible input states for which this post condition will be true. Similarly, here, given this precondition, x is less than or equal to y is the strongest that you can actually say about about this thing. So there is this notion of given a post condition, what is the weakest precondition that would be of interest, and similarly, given a precondition, what there could be several candidates that you can use as a pro condition to make the whole triple true, but the notion of what is the strongest condition would be is of interest. Okay, so let's move on. How about this? Ronald, can you take a crack? Here I'm asked the question, what program, give me a program such that this whole triple is true for that program. See,
Sir,
here
I might not be hearing correctly. Did you call my name?
I called Ronald.
Oh, sorry.
First, I'll ask Ronald, and then anybody can take a crack. See, what is this requiring? Ronald. If I start with X, it is requiring that when and if the program terminates for any input that is X greater than 0, false has to be true as a post condition. Can false be ever true? Can the formula, which is identical to false, be ever true? It can never be true, right? So, what kind of program can actually make this true? Now, can anybody answer?
Sir, would a non-terminating program work?
Exactly right. Who's that? Who answered this?
Ryan Hota.
Yeah, that's correct. Okay. So, Ronald, are you convinced now? See, because yes, the way these Hoare triples are defining partial correctness, and they care about the thing only if it is that the post condition ought to hold good when it terminates. So if it does not terminate, it doesn't matter what the post condition is, including false, and therefore this kind of Hoare triple is true only for non-terminating program. That's good. Okay, how about this? Here I'm asking for any program P, what is a post condition that makes this Hoare triple true?
Any
Uh,
condition?
Yes?
okay, I think we had opposite answer. Someone said I thought nothing can make this like valid or satisfactory.
I
Okay.
think anything is okay.
Yeah, there are two answers. Any predicate. Okay. So the second answer is correct because this is these are corner cases, kind of stumping kind of a thing. Because if it is false, then as you can see, but the definition of partial correctness, this is one of the cases where it is vacuously true. Okay, there are two cases where the definition of partial correctness makes the Hoare triple vacuously true. One is if it's non-terminating for any post predicate, it is true. Similarly, if your input predicate is false, then it is vacuously true. Therefore, anything satisfies any predicate would be okay. Okay, so remember that. So this is how it is defined. It's a logical implication. So if the logical implication is vacuously false, this becomes Hoare triple becomes true. And there are two cases. Okay, one is where the predicate P is false, in which case this is vacuously true. And that's what is happening here. Okay, so next one. Okay, anyone wants to take a crack at this? Is this true?
No, sir. It's
Yeah,
interesting.
this can't be true because this will keep it as, of course, in this case, false can never be made true. So, because no matter what, so this one, because it doesn't change the state of the world, the post condition has to be thing. How about this?
Anything will work, right?
Yeah, anything will work, including actually false. Okay.
Yes.
If it is false, obviously it is vacuously true because it is not constraining the post condition at all. So no matter what the program does, for whatever the inputs, okay, whatever input, because it is just not constraining the output at all. So yes, okay. So any predicate, good. Okay, so given this, and I have various other things that you can work on your own. So the way that whole now I'm going to be introducing inference rules, and you will see why even these inference rules, they obviously are defined much like in any logical system. You first define what it means for a whole triple to be true for the atomic, for the primitive statements, okay. And there you define it as just like an inference rule. It is defined with formula, some condition above a horizontal line. If that is true, then the triple that is given below the horizontal line has to be true. If the precondition is empty, then it means that it has to be true regardless of anything. So since skip does not, and it is in some sense parameterized with respect to the pre and post condition predicates that that you can actually use. So skip, given any predicate p for skip, this whole triple must always hold regardless of any assumption. So if you start with in a state that satisfies any predicate P after skip, that predicate P, you can guarantee that that predicate P will will hold good. Okay. Now, yeah. So similarly, you will have to define this for an assignment statement, which is the other primitive statement, and then build this define these what whole triples will hold good for these program constructors, assuming something holds good, already holds good for the programs subcomponents of your program. Before I show you the inference rule for an arbitrary assignment statement, which is how I have it here, but I want to go ahead and then see what it means for, yeah, I'm going to be doing slightly something differently, okay? Is for the conditional rule I had, sequential composition, okay? The rule for sequential composition in Hoare logic is as follows. Okay, you can read this in two ways. Okay, you can read it backwards or forwards. Okay, if here is a program that is composed that composes given two fragments of code Q and S, it sequentially composes them into uh, S being executed after Q. So the question is, how can I define what kind of Hoare triples that hold good for this? Now, when you view this backwards, you could say for the Hoare triple P, followed by 2, this Hoare triple at the bottom, in order for it to be true, then these two Hoare triples have to be true. Or if you read it in the forward way, if if you start with P, execute Q, and then R holds when it terminates, and when you have R and in the same state that satisfies R, if you execute S and T holds good, then you can conclude that if you started with P and executed Q first and then S, T would hold. Correct? That's what the sequential composition is saying. It is, in other words, saying if you want to prove something of a program that has two components that are sequentially composed, with the precondition P and the postcondition T, it is in order to prove that, if you can find some intermediate assertion R which holds good after you execute Q, and if in the same state that you start with the same state and execute S, T will have to hold good. So in order to, so that is two ways of doing it. So it's in this sense that it can be considered as defining the meaning of what it means to sequentially compose two fragments of code, okay, relative to satisfaction of Hoare triple, and also it gives a means to prove it, okay. Is that clear? Okay, the two ways of reading it.
Yes, sir.
Okay. Any questions there? Please ask. Okay. So because I might not have described it the best way, and if you're unsure about it, you can ask me can challenge me, and you can ask me what the thing is to explain it in a better way. I will, yeah. So this is how whole logic inference rules are, okay, except for the atomic thing. So with respect to and now you can see, given this rule, if you are somehow, you can decompose the for any program that is a straight line code, in the sense it is sequence of statements, straight line sequence of statements. You can use this repeatedly in to construct a proof of the entire program, and reduce that proof to showing that some triples hold good for individual assignment statement, okay. And that's how you construct the proof based on the syntactic structure of your program, okay. So that is the idea. So I will, given this rule, okay, I'm going to show you how. Take an example and make it bigger. Okay, so let's take this program. You want me to make it even bigger? So maybe I can. Okay, so this is what I have, the rule here. Okay, so let's suppose that I want to prove this one for. So here is a piece of code which swaps the values in the variables x and y. Okay. And I want to prove that to be correct. This is a program that has three individual statements, okay, assignment statements, and it assigns the value of x to a temporary variable z, and then assigns y to x, and assigns the original value of x, which is stored in z, to y. Just a simple swapping program. So how would you would expect, you can specify the expected behavior of this, intended behavior of this, using this pre and post. So if you start with a precondition in which x has some arbitrary initial value x naught and y has some arbitrary initial value y naught, then you want this post condition to hold good when it terminates, that x will have y naught and y will have the original value of x naught. So in order to use this inference rule, what it's as I explained it to you, so it says that in order to prove this of a composite program, which in this case is constructed using sequential composition, you need to find an intermediate assertion R, okay, in this case R1, such that R1 holds after you execute the first part of your sequentially composed program. In this case, it has two parts first, and then the first part itself is sequentially composed. So you do step by step. So if you can find an R1 such that this R1 holds after you execute the first program starting from P, and then you start from R1, and then you execute the second component, and you want Q holds. What could such an R1 be? Okay. So now an R1, if Q, yeah, what could such a an R is, what could such an R1 be? See, R1 you wanted to hold. If you had a post condition Q, then what could an R1? So this is assigning Z to Y, right? And Q is insisting so that X should be, this is assigning Z to Y. So, and Q is requiring that Y be X naught, right? And X be Y naught. And therefore, if Y has to be X naught, as Q insists, in the pre-state, it better be that Z itself has the value X naught, correct? Because Z is what is being chosen. That's what I'm saying. So Z better be X naught. And since this statement Y, this assignment statement leaves every other variable other than y, its value the same. And since you require that x be y naught in the post condition, it better be the case that x already have that value y naught, correct? Okay. And that's how that you have. So this certainly, if you choose R1 to be that, then you know that after you execute Y, Z, Q holds, correct? Any questions? So then all you need to do is to check if when you start with a precondition P and execute the first part of your sequentially composed program, if you end up in a state in which R1 holds. Then, as you know, the sequential composition rule says, then I can conclude that if I start with P and then execute the complete program, I end up with the given post condition. Now, so it is reduced now, the question to check if this Hoare triple holds, okay? This is once again a sequentially composed program, okay? So in order to use the sequential composition rule, you'll have to now find an intermediate assertion R2 and ask the question, is there an intermediate? Can I construct an intermediate assertion R2 such that when I start with R2 and execute the second component of the program, that is x is equal to y, I end up this in R1, okay? The R1, this is exactly R1. And when I start with P and execute the first assignment statement, Z is equal to X, I will be in R2. So So like we did earlier, you can analyze in order to ensure that this condition holds good after this assignment. What should R2 be? Because this is assigning y to x, and since yeah, so it is assigning y to x. So and since what am I saying? Yeah. So let me stare.
Sir, if z equals to x naught and x equals to y naught, R2 or something, can that be happen?
Yeah. So since y is being assigned to x and you want x to be y naught, okay, that y be better be y naught. That's what is happening. Okay. Y must be y naught. Okay. So the R2 that you have to construct, you can construct it this way. So y may be better, y must be y naught. And since z is not being changed at all, and you require z to be x naught, the same kind of argument. So you have to have z is equal to x naught. Then finally comes the question if you need to check if given that R2, if executing the first component starting with P, it holds. Now P is x is equal to x naught and y is equal to y naught. So in order to check, and you can see that this is obviously true because once again x the value of z which is required to be x naught better be x naught, okay, and y which is not being changed is equal to y naught, and therefore this is obviously holds. Okay, this is how this sequential composition rule, one way of interpreting how this works. Okay, so in general, in the when Hoare introduced these things, this is how the proof was working. Given some composed program, you need to construct intermediate assertions such that you could decompose the verification of Hoare triple for a composite program to checking Hoare triples for smaller programs. So, and obviously there is a little bit of a problem here. We need to guess what the intermediate assertions that you can construct, and they need to be of suitable strengths. Okay. They must be strong enough to prove the second part. The R1 must be strong enough to prove the second part when it is executed satisfies the post condition. But it has to be weak enough to ensure that when you start with the precondition for the entire program, like in this case P, the intermediate assertion holds after you execute the first part of your program. Okay. So to eliminate this guesswork, what you could do is there are two solutions. You can define you can always construct these intermediate assertions if you're working backwards, which is how we did here. Okay, we started with Q and then started guessing what the intermediate assertions was. And if you're doing it like that, then you make them the weakest precondition. So for a given Q, you can construct the weakest precondition that that makes this execution of the second component, the Hoare triple corresponding to the execution of the second component holds good. So you can choose to, when you're working backwards, you can always choose to construct that in the weakest fashion so that then you eventually get to something the weakest precondition for the entire program, and then you could check if your given precondition is indeed strong enough to prove the weakest precondition, the weakest precondition. Or you can work in a forward direction, and yeah, that's okay. So, or you can work from the forward direction from P, and you can construct the intermediate assertion such that you have, yeah, you always construct the strongest post condition corresponding to the given P condition and work your ways in the forward direction until you get to the strongest post condition for the entire program, and then check if that strongest post condition indeed implies your actual post condition for the your program. Okay. And in order to be able to do that, that's why you have another rule, a couple of rules, which are called the consequence rule. So if you want to prove something of P prime, this whole triple P prime QR, if you can, yeah, if you already know that you have an R that as a post condition that holds good when you execute Q in P, and if uh, yeah, P prime implies P. If you have starting with R, if you can come up with a weakest precondition, if you can come up with a P, which is implied by P prime, then you can conclude P prime. Or in the forward direction, if you get an R after executing Q, which is strong enough to prove your post condition, that is R implies R prime, then you can conclude. With this consequence rule, then your guesswork can be eliminated by defining the semantics, the whole rule, inference rule for an assignment statement, either in such a way that it gives the weakest precondition or the strongest postcondition for an assignment statement. And that's what is done here. So with that, by introducing the and I will stop today's lecture. So yeah, so we started with this. Okay, now the second one is the So here's what we actually, this is the rule that we use to construct the intermediate assertions. Okay, so this is the inference rule, Hoare inference rule, that defines what kind of Hoare triples are satisfied by an assignment statement. Now you have an assignment statement, say x being assigned the value of some expression e. Okay, this expression E can be defined over any program variable, including X. Okay, and you want some X, some predicate P to hold good as a post condition. Okay, over those variables. Then, what this thing says in general is P if P in which X, every occurrence of X in the formula, represented by P. That's what this thing is saying. If you replace every occurrence of X in P with E, the expression E, then that ought to hold good as a precondition. And as a matter of fact, this one is the weakest precondition that will make X is equal to E satisfy P as a post condition. Okay, that's exactly what it's saying. If P is to be true on the value of X, after it is assigned a value E, P must already be true on the result of you get of evaluating E in the pre-state. Okay. Now E can have other variables. So those variables will remain unchanged here, okay, in all those variables, because that's what X, this assignment statement leaves everything unchanged, okay? So only X, every instance of X has to be replaced by E, which is what we were doing. So because no variable except X is changed and E is evaluated in the pre-state, those are the two key points that you'll have to observe. So although it is kind of doing it backwards, it fits perfectly. Okay, and so that's why it is indeed defined in a backward fashion, and it defines the weakest precondition for P. So as you can see, this is precisely defining the effect of an assignment statement, while it is also giving a, a way of constructing the weakest precondition, okay, which is the stepping stone for constructing, bigger proofs as we saw, okay. So here are some examples. Okay, so if X is, I mean, I asked in at the beginning of the lecture, I asked you, what these question marks were based on an informal notion. I mean, after having introduced what Ho triple is. Now here, this rule is giving you exactly how to construct that. So what it's saying is, if your post condition is defined by this formula X greater than 0, what it's saying is, in order to get the weakest precondition, all you need to do is to replace every occurrence of X in this formula with the expression X plus 1. And that's exactly what is doing. So you can construct that, and that will be the weakest precondition, that X plus 1 is greater than 0, which is equivalent to saying X is greater than or equal to 0. Okay. Clear? Any questions? Okay. So now you can apply this to any assignment statement, okay? And if your programs are composite program constructed using sequential composition, and you saw how you could repeatedly decompose, you can use the inference rule corresponding to sequential composition to decompose, starting with the backward direction. You can construct the weakest precondition as intermediate assertion by pushing the P one assignment step at a time, and then push it all the way back to the entry point of the program, and then use the consequence rule to do it. Okay, and this is the rule that you will apply. Now, if you want to do a forward proof, then you will have to have a corresponding version of for an assignment statement, which defines the strongest post condition, which I will continue with in the next class. Okay. Yeah. Any questions you have so far? Of course, I'll have to give uh, a rule for the conditional statement, as well as while loop. Okay, that is there as well, and then that once we do that, it completes all the inference rules required for the toy programming language, the Hoare inference rules. Okay. Yes, I will stop here and ask if you have any questions. Okay, if not, thank you. Oh, by the way, I will be returning I'll be in transit next Tuesday. I'll be arriving only. Let me put these things just to announce, and I can announce that in the thing also, since it's getting late. So there'll be no class on Monday. So we will switch over to Monday and Friday because starting next week, it'll be all physical classes. So I'm assuming we'll switch over to Monday and Friday. So the next class will be on Friday. Okay. That is, that'll be the last day. That's okay. 26th, correct? Yeah. Okay. Yeah, you will get a note on that. Yeah.
Thank you, sir.
Thank you.